Alright, so you have just had your little discussion that you answered about why we have different or a unified set of measurement, why we have created a worldwide system of measurement. Why is that important? Well, the reason it's important is because years ago, before we had a unified system, each city, each country, each shop in a city, whatever, would have their different way of measuring things. And when money and commerce and all that stuff was done with the weight of precious metals like gold and silver, if something cost, say you were going to buy something and it cost you 3 pounds of gold, well, if 3 pounds of gold was one thing at this store, but then you went to a different place down the street and they had a different way of measuring 3 pounds that wasn't a standard between of what a pound was, then it was very, very difficult. The Roman Empire mostly got that taken care of because they overthrew everything, took over all this stuff, and changed a whole lot of basically instituted the Roman measurement stuff. But it really became an issue in the scientific age because, as we talked about in the scientific methods lesson, scientists will publish their results and then they share it with other people. They get their data, they get their results, and then they share it with other scientists who then look over it and will try and replicate what they did to see if they did a good job, see if they did a good experiment. Well, if you're using a different way of measuring than I am, it's very difficult to make our data work together and for us to see whether or not science actually works. So scientists figured this out, that having all these different measurements in different cities and different countries was a problem. So a group of scientists got together and they developed a system where we have a unified system of measurement for everything. And that's what we're going to be talking about today. So that system is called the International System of Units. Now this is in French, and I don't speak French, so I have absolutely no idea how to pronounce that. But since it is in French, because it was created in Paris by the Royal Society, but it is, the S is before the I, even though in English we say International System. It is called the SI system. So from here on out, you will always hear me say the SI system and not anything else. And it is the international agreed upon system. So they got together and they defined this. Now what they did was they decided, okay, what are the things that we have to measure all the time? And what are those things, and what is going to be the unit that we are going to use to measure it in? Are we going to measure it in feet or inches or miles when we're talking about length? And so they created what are called base units. And a base unit is defined a unit in a system of measurement that is based on an object or event in the physical world and is independent of other units. So they actually had physical objects that they said this is what this is going to represent. So when we talk about mass, the kilogram, there was actually a physical mass. It was actually called the international standard, the international mass standard, that it was just, this physical object. This is a kilogram. And then all other kilograms were based off of that one. And this is a meter, and all other meters were based off of that one. So to better describe the range of possible measurements, scientists added prefixes to the base units. And those prefixes, which we'll see on the table on the next slide, are based on factors of 10 and can be used with all SI units. So these are the 7 SI base units, the quantities that they measure, and what the unit is with its symbol. So time is measured in seconds, and the symbol is an S. Length is measured in meters, and the symbol is an M. Mass is measured in kilograms, and the symbol is kg. Now this one is a special one. It's the only base unit that has a prefix on it. We'll talk about that more in a little while. Temperature, the base unit for temperature is Kelvin. Although we talk about Celsius a lot, and we use Celsius a lot in science, the actual SI unit is the Kelvin, and we will get to that at some point. Amount of substance is the mole. This is one of the biggest things in chemistry, so this one you really need to know. Electric current, luminous intensity, we don't really have to worry about those because those are things that you will do in physics if you take physics. So those are the base units, and they're all actually based on physical things. We'll talk about that in a little bit. These are our metric prefixes. So our metric prefixes, there are more than this, and we're going to get into some of those in a little bit. I will show you the others. This table just has the biggies that you use. You're used to seeing giga and mega, like gigabytes and megabytes for your computer stuff, and kilo, and then there's deci, centi, milli. Your base unit goes here, so like meters is 1. So a kilometer is 1 times 1,000, or 10 to the third. So a kilometer is 1,000 meters. A gigameter is 1 billion meters. So you'll notice that there's 1,000 here, there's a million here, there's a billion there. So that is the prefix. Now going the other direction, going smaller, a decimeter, so D with an M, decimeter, is 1/10 of a meter. A centimeter is 1/100th, which means there are 100 centimeters in 1 meter. All of these are based on multiples of 10. So to go from one to the next, all you do is multiply or divide by 10, which is really easy. And that's why the metric system is superior to other systems of measurement that require fractions and stuff. Like if I wanted to go from an inch to smaller units, you have inch, and then you have 7/8 and 3/8, and it becomes all this fractions of halves and fourths and all that stuff. And let's face it, if you're adding them all together, you can more or less add numbers with decimals fairly easily, but adding fractions is a bit of a pain in the butt. So the metric system is a whole lot better. Alright, so let's talk about these base units a little bit. So the base unit for time is the second, and it is based on the frequency of radiation given off by a cesium-133 atom. We'll talk about radiation more in a couple weeks, but this is what the second is based off of. So that click of the metronome of 1 second is the time it takes, or the frequency of the radiation that is given off. That's what they decided to base it off of. Base unit for length is the meter, which now it is the distance light travels in a vacuum, and 1/299,000th or 1,792,458th of a second. Basically 300 million. Because light travels 300 million meters in a second, so the distance light travels in 1 second, that is or in that 1/300,000th of a second, that is what a meter is. That's what it's based off of now. They changed it a number of years ago. Originally, the meter was based on 1/10,000th, I think it is, the distance from the North Pole to I think Paris, running through the prime meridian. I can't remember exactly. Maybe I'll look it up later. The SI base unit for mass is the kilogram. It was originally based on a mass of the international kilogram prototype. It's now defined by something called Planck's constant. We'll actually talk about what Planck's constant is in a few weeks. So this actually was the last of the SI base units to be redefined. All of them were redefined in the last 30 years. The kilogram was the last one to be redefined, and they actually just officially redefined it back in 2018. It was actually kind of a big deal. Maybe at the end of this video on the page, I will link a video to a video about that, because it's actually pretty interesting. The SI base unit of temperature is the Kelvin. Even though we use the Celsius temperature scale a lot in class, Kelvin is the SI base temperature, and Kelvin and Celsius are very much similar. We'll talk about that in a little while. 0 Kelvin is the point where there is virtually no motion or kinetic energy. We also call that absolute zero. It's the lowest possible temperature. And later in the year we will talk a lot more about why that is and what that means. But right now, that's why we use it as the base, because it is based on something that cannot go any lower, so it's pretty cool. Kelvin is actually nice to use because you never have to worry about negative temperatures in Kelvin, because if you can not get any lower than 0, then you can't have negatives. Two other temperature scales are Celsius and Fahrenheit. We will use the Celsius scale in this class in chemistry. However, we are not going to use Fahrenheit, and for whatever strange reason, the United States is actually the only country in the world that still uses the Fahrenheit scale as their major measurement of temperature. So these are just a picture of our two different temperature scales. A Celsius degree and a Kelvin are the same size, they just start in a different place. And again, we'll talk about that more in later. Now, derived units. We have base units, or units that are actually based on something in the physical world. A derived unit is something that is made up or made out of. When you derive something, you make it out of something else. Not all quantities can be measured with base units. So you notice there are only 7 base units. You have time, length, mass, amount of matter. Those can all be measured, but we can't measure, volume wasn't on that list. So speed wasn't on that list. So a unit that is defined by a combination of base units is called a derived unit. So speed is a good example for that because you're familiar with it. Meters per second, that's how, or miles per hour. Meters is a unit of length, seconds is a unit of time. So you have length per time. So I'm taking the two base units and putting them together to make a derived unit, meters per second. All right. Another quantity that is measured in derived units is volume. So it's measured in cubic meters. Because when we measure the volume of something, you're going to have like these cubes. It's 1 meter by 1 meter by 1 meter. So volume is length times width times height. So we have 1 meter times 1 meter times 1 meter is 1 meter cubed. So it's a cubic meter. However, each of these meters can be broken up into 10 smaller things. So I've got 10 decimeters here. So a deci is a tenth of a meter. So I have 10 decimeters here. I have 10 decimeters here and 10 decimeters here. So in this big, huge cube, there's 1,000 decimeters. All right, or 1,000 cubic decimeters. So there's 1,000 of these littler things. So if I make that one bigger, each decimeter can be broken up into 10 centimeters. And so there are 1,000 centimeters, cubic centimeters in this cubic decimeter. And come down, you got millimeters. So you got cubic millimeters. There's 10 millimeters here, 10 millimeters here, 10 millimeters here. That's 1,000 cubic millimeters in this cubic centimeter. So I have 1,000 of these little guys inside this one, and 1,000 of these inside this one, and 1,000 of these inside this one. So you have to go from millimeters to millimeters cubed to decimeters cubed. Sorry, let me start that over. To go from millimeters cubed to meters cubed, you multiply by 1,000 3 times. That's a lot. So that being said, a cubic meter as our standard measurement for volume, that's a huge volume. Normally we talk about things in liters and whatever. So a cubic decimeter is actually what a liter is. You're familiar with a liter, like you buy a 2 liter of Coke. That's a cubic decimeter, which a cubic decimeter, there's 1,000 of those. So think of taking 500 2-liter bottles and filling up something. That's how much a cubic meter would be. 500 of those 2-liter bottles. You don't want to have that be your normal thing of measurement. So we don't use the cubic decimeter that often, or the cubic meter that often as our measurement. Instead, for everyday use, we use the liter, and a liter is 1 cubic decimeter. So dm to the 3. That's 1 liter equals 1 dm cubed. Okay, so a liter is a cubic decimeter. We're going to use liters a lot in this class because we measure a lot of volume. Density is another derived unit, and it is an extremely important one in chemistry. So it's measured in mass per volume. Typically in chemistry, we're going to use grams per cubic centimeter. So it's the amount of mass per unit volume. It's the amount of mass you have per volume. Density of substance usually cannot be measured directly. Usually it's calculated. So we measure its mass, we measure its volume, and we calculate its density. We can't actually measure the density of something. So you calculate it using this following equation. Density equals mass divided by volume, or density equals mass divided by volume. And with that, we are going to, I'll do some examples of some metric conversions for you in just a moment. And maybe some examples of some density calculations. So stay tuned, and maybe on the back of your notes or on another page of your Google Doc, if you need to open that up, you can work out some of these examples or just watch the video multiple times. But for now, that's the end of the notes that we're going to do for today. So, oops, went too far. We will pick up in your notes on your assignment or on your printout with the next video. So right now I'm going to go into doing some examples for you, and so you can see how to do those metric conversions and all that stuff a whole lot easier.
Alright guys, now that you have done a brief overview of the metric system and measurement, I'm going to do a few examples for you of how to do those metric conversions. It's going to have a few prefixes that are a little bit different than the ones that were in the PowerPoint, but that is fine, and you will hopefully understand how to do the metric stuff a little bit better. I'm also going to do some examples of density problems since those were in the discussion as well. So keep that going and be prepared to be wowed.
Alright, so now we're going to do a little bit of examples of that metric system stuff. So I'm going to show you something a little different than what was on the PowerPoint. We have the prefixes, and this is kilo, hecto, deca. This is your base unit, deci, centi, milli. These are the most common ones that we're going to use. We will use some of the other ones that were in the PowerPoint, but this is going to be the most common one. So you can remember this by King Henry died by drinking chocolate milk. That's your base unit. All right, so this is where you would put seconds or minutes or grams or liters or whatever, grams, liters, meters, your base there. And to move from one to the other, we simply move the decimal. So let's say I wanted to convert or find out I have 375 decameters, and I want to know how many millimeters that is. All right, so I have 375 decameters. Well, deca is here, so to go from deca over to milli, I move 1, 2, 3, 4 places to the right. So I'm going to take my decimal that's right here and I'm going to move it 1, 2, 3, 4 places to the right, and I fill that in with zeros. So the answer here is 375 decameters is 375,000,000. So that's 3,750,000 millimeters. Okay, so that's pretty simple. If you simply write out the King Henry died by drinking chocolate milk, King Henry died by drinking chocolate milk, or kilo, hecto, deca, base unit, deci, centi, milli. Those are your prefixes. Then you can get all of that. So that is our first example of how to do that. All right, so let's do another example. On this one, I have written out the names of those prefixes for you so that you can see that. So this time, let's say we want to know, we have something that is, say, 3.05 centimeters long, and I want to know how many kilometers that is. Or let's not use meters. Let's say centigrams. So 3.05 centigrams, and I want to know how many kilograms that is. Well, so to go from centigrams to kilograms, I'm going to move from here. It's 1, 2, 3, 4, 5. So I'm going to move 5 places, and I move to the left. So I'm going to take my decimal, and I'm going to move 1, 2, 3, 4, 5 places to the left, giving me the decimal, and then 1, 2, 3, 4 zeros. And I still write the 305 because I still had the 305 there. So 0.00000305 kilograms. That's my answer that goes in that blank. Now you should notice that this is a very small number because a centimeter is a small unit. I mean, a centimeter is only like that big. So 3 centimeters is, this 3.05 centimeters is a little over an inch. So a kilometer is a little over half a mile. So it should be a really small number because there's not very many kilometers or kilograms. Sorry, I'm still have meters on the brain. My bad. You get the point. Regardless of what the base is, the prefixes work the same way. That's the joy of the metric system, is the prefixes work the same way regardless of which base you're dealing with. So that's example 2, and give me a second. For our third example, let's do something that actually starts with the base unit. So let's say I have 5.06 liters, and I want to know how many milliliters that is. Well, I have liters to milliliters, so liters is my base. The way you can know if it's the base is you'll notice each of these prefixes is a single letter, right? And each of your, for the most part, your base units are single letters. Like we have seconds and meters and grams. That's the base that we're going to talk about here. So we have seconds, meters, grams, liters. These are all one letter. So if you only have one letter, then it's your base unit most of the time. All right, there are some exceptions that you'll get used to as time goes on, but if it only has one letter, it's your base. If it has 2 letters, then one of those is the prefix and one of those is the base. So milli is my prefix, liter is the base, so that's a milliliter. So I want to go from the base, liters, to milliliters. So I'm going to go 1, 2, 3 places to the right. So I'm going to take my decimal, I'm going to move it 1, 2, 3 places. So I have 5060 because I've moved it 1, 2, 3 places. So that is my answer. So 5060 milliliters, and that is how we move in the metric system. And if you remember this order, then it's really easy. Just wherever you are to wherever you're going. That's how many places you move the decimal and the direction. So if you always write it like this, then you always know whether you're going to move to the left or to the right. If I'm at deca and I want to go to centi, I move 1, 2, 3 places to the right. If I'm at deci and I want to go to kilo, I move 1, 2, 3, 4 places to the left. Don't forget the base. Don't forget the base. Because it is a place that you have to go. So that is how you do metric conversions. Okay, so now let's look at a density equation calculation problem. This is not really complicated math, but I'm going to do an example for you here. So let's say an object has a mass of 65 grams and a volume of 18 milliliters. What is its density? Well, our equation here, density equals mass divided by volume. So I have density equals mass divided by volume. So I'm simply going to plug these numbers in. My mass is 65 grams. So I have 65 grams divided by 18 milliliters. And divided by is like a fraction, so that's why I'm writing it like a fraction for those of you that aren't familiar with that. So I'm simply going to do 65 divided by 18. So you have a calculator function, and a little bit later I'm going to give you directions on how to download onto your Chromebook a extension that will allow you to use a TI-80 graphing calculator on your Chromebook, or TI-84. But for right now I'm just going to use my phone's calculator because it's adequate. So I have 65 divided by 18, and it gives me 3.611111111. Now I want you to always round all of your answers until I tell you otherwise. Always round to 2 decimal places. So I have 3.61, and that 1 is less than 5, so I'm going to leave it and not round up. So I have 3.61 is my number, and the unit is exactly what I have written here. It's grams per milliliter, because I did grams divided by milliliters. So whatever math you do with your numbers, you do the same math with your units. You just write that out. And you have to include your unit when you're writing your answers on paper. Now, a lot of the stuff that we're going to do online, I'll have the unit there for you, but just remember, a number without a unit is meaningless, so we just have to have a unit there. So there is our answer for the density problem. All right, now I'm going to show you how to do a density problem where you're not solving for density, still using this equation. So we're going to have to do a little bit of algebra, which I know might scare some of you, but it's not all that complicated if you just follow the process, follow the steps, and do what I do. So we have an object has a volume of 12 milliliters and a density of 2.6 grams per milliliter. What is its mass? So I'm going to write over here what they told me. They told me it has a volume of 12 milliliters and a density of 2.6 grams per milliliter. And I want to know what is the mass. So then I look at my equation. Density equals mass divided by volume. Well, the problem is my equation says density equals. I want my equation to say mass equals. So I need to move this volume over to the other side. And the way I do that is by multiplying. Since volume is being divided right now, I'm dividing by volume, so I'm going to do the opposite of division, and I'm going to multiply by volume. And if I do that on this side, the volumes are going to cancel out, so they disappear. But whatever I do to one side of my equation, I have to do to the other to make sure it stays equal. So I multiplied by volume over here, so I have to keep multiplying by volume on the other side also. So now my equation, these volumes have canceled out, so now my equation is density times volume, it doesn't really matter what order you write them in, equals your mass. So now I have something equals mass, which is what the question wants. All right, and back to the it doesn't matter what order you, 2 times 3 and 3 times 2 are the same. It doesn't matter what order you write them in. I just like to write them in alphabetical order. That's a personal preference of mine. There's no rule I don't know of that says you have to. Anyway, now that I have the correct equation, now I'm simply going to take my numbers and plug them in. My volume is 12, and my density is 2.6. So I'm going to do 2.6 grams per milliliter, and I'm going to multiply that by 12 milliliters. All right, so again with the calculator, we have 2.6 times 12 gives me 31.2. All right, so I have 31.2. I said always round to 2 decimal places, so if there's only one, then just add a 0 there. So 31.20. And what's my unit going to be? Well, this is grams divided by milliliters. So I have grams divided by milliliters, and I'm multiplying it by milliliters. And just like we saw up here, if it's multiplied and divided, then it cancels out. So what I'm left with is grams. So my unit is grams. And I just realized you couldn't see what was underneath all of that. So let me show you again up here what I did. I have grams per milliliter, and I multiplied it times milliliters. So grams per milliliter times milliliters. Milliliters are multiplied and divided, so they cancel out, and you're left with grams, which is why that is the unit in your final answer. All right, so this problem is the hardest of the kind of the density problems. But if you follow the process, it's not that hard, and you'll notice that I kept the numbers the same. All I did was change that this now has an object has a mass of 12 milliliters and a density of 2.6 grams per milliliter. What is its volume this time? So I'm still going to write down what they told me. So now I have the mass is 12, and that should be grams instead of milliliters. So the mass is 12 grams, and the density is 2.6 grams per milliliter. This time I want to know what the volume is. So again, I have density equals mass divided by volume, but I want it to say volume equals something. I don't want it to say density equals something. So I have to get my volume to be on the one side by itself. The problem is it's also, volume is also in the denominator, the bottom of the fraction. So I need to move it to the top of the fraction first. You can't have it be volume equals if volume is in the bottom. So the first thing I need to do is exactly what I did on the last problem, so that I can move my volume to the side, okay, or out of the bottom. So now I have volume times density equals mass. So this time I want to get volume by itself, so I need to move the density. Well, density is being multiplied, so I'm going to divide. When you divide by d, the d's will cancel, and I have to do that on both sides. So now my final equation is volume equals mass divided by density. So that means I'm going to take my volume is going to equal my mass, 12 grams, divided by my density of 2.6 grams per milliliter. And so again, we take our calculator, and now we're going to do 12 divided by 2.6, and that equals 4.615. So that's going to round to 4.62. So my volume is 4.62, and notice the grams are on top and bottom, so they cancel. Milliliters is the only thing that's left, and so that is my final answer. So now that we're done with all of the examples in the notes today, you're now going to move on to your assignment. So make sure that you have and are all ready to do that. And if you have any questions about the assignment as you go, please feel free to ask me, message me, get on our Zoom. Be ready to, don't be afraid to ask questions. Yeah. So have a day.